Our speaker today is Dr. Jack Atkinson from University of Cambridge. Jack is a senior research software engineer at the Institute of Computing for Climate Science, and he's going to be talking to us today about coupling PyTorch to Fortran. Yep. So without further ado, Jack, I'll hand over to you.
Cool, thank you. So yeah, I'm here, as Donald said, I'm at the Institute of Computing for Climate Science, working as kind of research software, but we work with a number of different projects looking at doing different things with climate software, be it modeling, sort of data processing, and then a lot of people have are kind of looking at applications of machine learning within these. And so what I will talk today about is kind of some software that we developed sort of in response to this, which was people trying to embed machine learning components within larger Fortran models, but kind of experiencing difficulty or problems with that kind of coupling process. And so we wrote some code to make this easier, and that's then kind of grown into its own library with a few more things since. So I have got the slides online if anyone wants to follow along with anything, or click the links later on, and I think I put them in the chat for people on Teams. Oh yeah, sorry, there you go. So yeah, I hinted a little bit about the motivation of this work. So our particular background comes from looking at kind of weather and climate models, which are these large sort of multi-component systems, sort of traditionally very, very large codes being run on large computing systems, usually something compiled, and a lot of them written in Fortran, sort of for historic reasons. Yeah, these are often sort of many component systems, but what I want to contrast with and the sort of largest bit of uncertainty within these is sort of things that happen at a subgrid process. So when we're running climate models, the traditional way to do things is kind of break the atmosphere or the ocean or whatever we're modeling up into a series of small boxes, and then solve some sort of PDE equation across those boxes with finite elements, finite difference, something else. But there's always going to be some processes that occur kind of within those boxes that are at scales smaller than that grid that we can't capture with a PD or something else. So typically in sort of atmosphere, which is where my background is, this would be kind of cloud processes. So we say within our 100 kilometer box, we've got some moisture content, some water vapor, but how that water content is distributed within that 100 kilometer box can vary. So it could be kind of one giant sort of superstorm system. It could be lots of different kind of cumulus clouds scattered around, and it could be distributed at kind of different heights as well. And depending on exactly how that is, can have a knock-on effect on the behavior we would expect to see, sort of where that heat is moving. And so we have to come up with some kind of model for the behavior at below the grid cell level. And this is traditionally done sort of with parameterizations. So if you're familiar, this might be kind of convection parameterizations, microphysics parameterizations, and this kind of goes all the way down to modeling the smallest scales within those processes. And this is sort of typically sort of the largest sources of uncertainty within a lot of these kind of big finite element models. And the same is true in sort of other fields. So my background's kind of weather and climate, but if you're looking at sort of materials modeling or molecular modeling, the same sort of ideas apply. You're solving PDEs, and eventually there's some scales that have to be represented with some other parameterized or sort of empirical model. So this contrasts slightly to sort of machine learning and climate science, which, there we go, with machine learning more generally, where often kind of the application we think of with deep learning is that we have some inputs, we feed those inputs into a neural net, and we get some answer out the other end that we then use to make comments or say something about. And within kind of weather and climate and other fields, there have been some attempts to do stuff like this. So when we had sort of the rise of the weather forecasting emulators, so things like ForecastNet, Pangu Weather, GraphCast, these were operating sort of on that principle where you fed some kind of weather data in, it went through kind of a big machine learning process, deep learning, and spat out the results that we're interested in at the end. But what I'm interested in sort of here is slightly different, which is rather than replacing this entire kind of scientific or decision process in the middle, we're actually looking at just replacing one component of that much larger Fortran or compiled model. And so in this case, we sort of say we'll take our Fortran dynamic core, we'll take all of these other parameterizations, and the only thing we're going to replace with some kind of machine learning is just this single convection parameterization. And there's a few things, or a few reasons people are interested in doing this. One is perhaps you have just a very, very computationally intense process. So if this is forming a bottleneck in your code because even kind of your parameterization model is still quite complex, typically sort of radiation's quite famous for this, you might say, perhaps I can get some speed up if I just emulate exactly the same process that I've got, but now by running a neural net, I can do it in a much faster time. The other interest that some people have is to say some of our models sort of make quite sweeping or quite coarse predictions. So kind of you think maybe some of the parameters in gravity wave models sort of make assumptions for a parameter that we assume sort of holds true across the entire planet. And so people are saying, actually, with the wealth of data we have out there, perhaps we can learn things from real world data to represent these subgrid processes and then sort of model them more accurately, which will then have a knock-on effect in sort of the results of the broader model, making our predictions more accurate. And then sort of anything in between that scale. So it's usually kind of scientific accuracy and speeding up computation time that people are after. However, kind of trying to do this hybrid modeling approach with a mixture of things brings a number of challenges. So there's one which is kind of reproducibility, which is this idea that if we've trained some machine learning scheme somewhere else, we want to be sure that it's going to perform the same when we put it within our broader climate model as it did wherever we trained it. And that's kind of not necessarily trivial, especially if there's lots of steps we have to go through to actually couple it up together. There's also kind of the question of reusability. So with kind of a conceptual model or kind of an equation-based parameterization, typically you could take the equations of that subgrid model, and as long as you're sort of not going to extremes with it, you can apply that in a range of different models with a range of different grids, grid cells, different resolutions, etc. Whereas with the machine learning models, kind of if they've learned on a particular grid or a particular resolution, you begin to get problems of kind of those parameterizations suddenly being locked to the places they were trained in. And so there is some stuff we've been looking at with this, though I won't talk about it explicitly today. Because the main problem I'm kind of going to focus on in this talk is the language interoperation. And so what's behind this is the fact that traditionally in machine learning, a lot of our frameworks, a lot of our work is done in Python, so using either PyTorch or perhaps not so much recently TensorFlow. These kind of very, very advanced frameworks, they've got a lot of features, they make it easy for people to go through the process of developing neural nets, training things, etc. But in contrast, a lot of the models I've been talking about, particularly, as I say, in the weather and climate domain, are written in Fortran. So these sort of include the at the Met Office, or moving now Elfric, the IFS at ECMWF, or the German weather system ICON, all Fortran-based models. And so the challenge here is, how do you take something that's running and working in Python and use it to generate data, read data within that larger Fortran model? So there's a few ways that this can be done. So you could implement your neural net in Fortran. At the end of the day, if we're talking sort of linear layers, particularly linear layers, it's just matrix multiplication in it. So Fortran is very, very well suited for matrix multiplication. And it's not sort of an excessive stretch to sort of write your ReLU functions with sort of modulos or if else's. However, this does then create additional work, because if you've already written and trained your NED in Fortran in Python, you've got to then rewrite that in Fortran. There's also, as I said, reproducibility problems of how do you know that just because you think it looks the same, how do you guarantee that it definitely is? And then sort of linear layers and feed-forward nets are fairly old in this domain now. People are moving to much more interesting architectures, things like concurrent nets, and sort of a lot more exciting things. And these are going to be much harder to implement in Fortran. And so if you're kind of writing your own software to do this, you're never going to keep up with what Meta or Google are doing within their frameworks. And you're also probably not going to achieve the optimizations that they're achieving as well with that code. Alternatively, there's a sort of Python script called ForPy. So this is on GitHub. It's actually for what you want to do. It's really nice. It's kind of a single Fortran module. You can drop it into your code, compile with it, and it will give you access out to kind of Python runtime. So if you have a Python script in a Python environment, you can sort of pass data between Fortran arrays and that Python script, run that script in Python, and get things back. The disadvantages here are that it's really just kind of a Python interface. It's not been designed kind of with machine learning applications in mind. It's also GPL licensed, which could cause problems depending on exactly what your project is if you want to include it. And it's also sort of not had any updates in, I think, the last 5 years. I'd have to check. The SmartSim, which is kind of a tool developed by HPE, which provides this kind of Python control center and then allows you to pass data between Fortran workers and Python workers over an API. This is quite good, but there's sort of a steep learning curve and there's a lot of data copying between simulations, which can get sort of very expensive, especially if you're dealing with large arrays. And then finally, there's the Fortran Keras bridge. So this is specifically for TensorFlow, which now, particularly in kind of the science and research community, I think people have moved over to PyTorch predominantly. And also, again, this I feel would fit the definition of abandonware at this point. It's not been updated for sort of the latest TensorFlows, at least. And then sort of since we've been doing this work, there's a few more options that have grown. So TorchFort is kind of similar to what we do. That's developed by NVIDIA. There's also these two libraries which are seeking to put kind of machine learning stuff natively into Fortran. But again, sort of they're playing catch up to most bigger things and don't have as much of the resources they do. So the other thing to talk about when we were looking at developing this code is efficiency. So I think often when we talk about efficiency within computing, we sort of think of the computational performance efficiency, sort of how fast can something run, how quick, or sort of how quick is the data transfer, how many sort of simulation steps can we do per hour of wall clock time. But within research, I think it's also important to think about the developer efficiency. So here, kind of, we're not focused on just running repeated simulations every time. What we're actually trying to do is facilitate it so that people doing research, developing a range of different machine learning schemes, can fit them into existing Fortran models without having too many headaches, without having to worry about how do I do language interoperation, leaving it so they can just focus on making changes to the machine learning scheme and then coupling it relatively easily and seeing how that has a knock-on effect in the results in their larger models. And so this has been sort of a focus very much as well whilst we've been developing this library, in terms of providing good documentation, good tooling, kind of doing as much as we can to lower the burden on the users, and do things sort of behind the scenes as well. But we also have a focus on the computational efficiency, and I'll talk about some of those things there as well. So that brings us on to FTorch, which is the library we've been developing. And the way kind of we're approaching things is to take PyTorch models that people have researched and developed, trained offline, and provide an interface for them to bring them into sort of a generic Fortran code system. The way we're able to do this is that PyTorch really is sort of almost could be viewed as a Python front end to what's actually a big C++ library called libtorch. And so this is partly why PyTorch is so fast, is really underneath. It's a lot of compiled code. And very nicely, what sort of PyTorch have done is they've made the C++ code available and provided kind of a application programming interface or API into that we can use. So with that in mind, it's also relatively straightforward since 2003 to make use of C++ or C code from within Fortran. The ISO C binding was brought into the standard, which provides you with a way of writing nice interface functions out to C++ libraries if you've got a nice API. So what we're doing is providing essentially a set of Fortran wrappers around that C++ API to facilitate a Fortran API to users with a few extra bits in there that I'll go into. The way this sort of will typically work is users save a PyTorch model that they've been developing into a format called torch script. And it's this model that's then saved can be run by the C++ code through the C++ interface. And then, yeah, like I say, we provide this Fortran API by wrapping around the C++ API. And so thinking about some of the other approaches I mentioned previously, the typical route sort of researchers we've worked with were generally going down was to take their Fortran code, get the data out somehow. So perhaps writing it to file, writing it to disk, or maybe with 4Py at least, sending it through a data type to an external Python interface. They would then call some kind of Python runtime, which would spin up their machine learning script, run the script on that data, again, put that data out somewhere, send it back to the Fortran, away we go. And all of this, of course, has to be managed from within some kind of Python environment or Python system. And given that a lot of these Fortran codes are running on high-performance computing systems, managing that Fortran environment can get sort of progressively more and more complicated. I think XKCD summed it up quite nicely. But it's not super desirable to be trying to manage this on a high-performance computing system. And at the same time, like I say, you've got to worry about kind of incurring data transfer overheads with a number of these approaches as well. So instead, as I say, what we're trying to do is look to go directly from the Fortran to the underlying libraries without worrying about kind of that Python runtime. I mentioned both the computational and developer efficiencies. Some of the things in this library, so we've made it easy to obtain, but also easy to build. So it's available on GitHub. You can get it here. Clone it as you would do most things. But the build system we've put in there is driven by CMake. So rather than having lots of sort of different make files and people having to get the code, but then adapt a make file for their system, worry about all these things, hopefully, as long as they can set some environment variables and we give sort of documentation on how to do that, you should then be able to build fairly portably using the CMake build process. And this has also allowed us sort of relatively simply to map between doing both Unix builds and supporting Windows builds as well. In terms of linking, so we provide the infrastructure coming out that would enable users to easily build and link to FTorch if they're building with CMake. But a lot of the models kind of people are trying to use this in are still using older makefile or shell script processes. And so if that is the case for your particular application, we've got some documentation, but you can link it into your compiles or link it into your builds, much like you would do with kind of any other library, say netcdf, by just providing a compile flags and linker flags as well. So if you're using makefiles, that's also an option. We then got some user tools, so this will make more sense in a moment, but we provide kind of some tooling to actually help users take the models that they've developed within Python and save them out into the appropriate torch script format with only minimal modification, kind of to make it as smooth as possible. And so one of the, I think the most important things about the work we've done is we've got a very, very comprehensive example suite, and a number of people we've kind of worked with or have used the library since have cited this as being one of the main reasons sort of they moved forward with using this software, is because for kind of, we break it down for all the different things you might want to do. Goes all the way from kind of just saving a very, very basic net, adding in kind of looping, convolutional networks, hardware acceleration. So we do lots and lots of step-by-step that's very, very well guided. And I think this has really helped us with kind of getting that adoption by other people in the community. And then, yeah, we've got a full API on documentation online. So this is built using Ford. So it's kind of auto-generated from the documentation within the code, along with any additional stuff that we've written, kind of guiding users through how to use it. And then, yeah, finally, as I said, it's sort of licensed under MIT, so you can relatively well do what you want with it. And we're open source on GitHub, so if anyone's welcome to make contributions or raise issues, this sort of thing. So coming on to kind of the computational side of things, one of the really nice things about the way we're approaching this by using that kind of underlying libtorch C++ library is that we're actually using everything PyTorch or libtorch has written themselves. So any optimizations they've built into that code, we're running with that. Any kind of new features should filter through and become available sort of as long as we can make an API for them. And sort of any more esoteric or more exciting machine learning things that are beyond what I know about machine learning should be available to users if they want to use them. The other thing about this is it also means that we get better reproducibility. So rather than writing a net, training a net, writing something else in a different code base and hoping it matches or stays the same, now, as long as kind of data is being passed the correct way, people are running the same net that they were running in PyTorch. So should get the same results out. And then similarly to this, so if we want to make use of hardware acceleration, this has already been implemented within PyTorch or within libtorch. So again, we make use of kind of the existing backends in the libtorch code to do this. There's a little bit of extra work we have to do on our side to pass the data across, but much of kind of the hardware, we didn't have to write any CUDA, we don't have to write any sort of HIP specific code. We're using what's already there underneath. And we've got, yeah, currently CUDA, the ARM HIP, also the Apple Silicon there's a backend for, and the Intel GPU hardware as well is currently in there. The next one, so one thing people always sort of bring up with this kind of Fortran to C++ interfacing is the issues with row major versus column major. So in Fortran, I'm potentially going to be in trouble here, your arrays are column major. No one's corrected me, which means that in sort of, if you have a 2D array, everything will just be one long line of numbers in memory. But that line of numbers will be constructed by running down each column. Whereas in Python, C, C++, we've got the opposite, which is row major. Everything will be constructed by running along. So there's a danger here that you need to sort of be very careful that when you write or have something in memory that's being read by Fortran, and the same thing is being read by C, C++, Python, you get a transpose of your data. And so some of the earlier projects we've been working with have kind of been taking great pains to do these transpositions before they wrote anything out and sort of having to check all of this. But again, if you've got a lot of data, sort of that transposition process, particularly for a very large array, can get quite expensive. The nice thing we've got is that we sort of some of the extra source within FTorch is that we abstract a lot of this stuff away from the end user by using kind of strided access. So as long as we can infer the shape of the array that they're passing through to PyTorch, we can tell PyTorch to read it sort of jumping in the correct order as appropriate. So the user no longer has to worry about this, and it's no longer a potential pitfall, though we do have kind of a more advanced interface underneath, which does provide you more control over this if you so wish. And finally, we've got no copy access in memory if people are running on the CPU. So this is sort of the idea that the data that is being used by Fortran, your Fortran arrays appear, it will be stored somewhere in memory, rather than having to do data transfer or pass data, generate copies of that data, which again could be expensive if it's particularly large. We tell PyTorch just to look directly at that data and interpret it in the correct way within the libtorch API. So there's no kind of overheads incurred with copying this. So I guess what, or at least within the RSE audiences, what people really want to look at is some code. So here we go. So I said we need to I'll sort of ease people in and sort of think about the process as you would go through this if you wanted to use it in your model. So we start off with some kind of model in Python, and we need to save it to this torch script format. And torch script, as I say, it's kind of this statically typed sub-language of Python, which means that it can then be read and understood by sort of C++, which has a bit more rigor on what it needs to do with different things. And it can then be read by the C++ interface into Torch. So typically, the first thing we need to do is get a model. So here we've pulled in ResNet 18, but in your work, you would substitute this for whatever your particular model is loading in your particular set of trained weights. And then you put it in sort of eval mode to set some optimizations and turn off some of the kind of back propagation processes. The next thing we need to do is take that model and save it to Torch script. And there's two approaches of doing this. One is by tracing. This is where you generate some kind of dummy input and run your model with it. And what PyTorch, or what the what the tracing process will do is it'll just take that array that you put in and kind of trace the operations as it moves through your net to construct some operations that describe what's going on. This works quite nicely if everything is kind of nice and linear through there, but it's going to have problems with conditionals because you can't guarantee what branches you're taking for just some dummy input. So if you have a more complex net, then there's also the option to do scripting, and this is more involved, but will actually look at the code in your PyTorch model and convert it into the equivalent Torch script. So once you've done that, it's then a process of freezing, which just enables some optimizations, and then saving out to sort of a blob or a binary object there. So the end result of doing all of this is that you've got this saved model.pt somewhere in your system. And a good question that someone asked for the first time at a workshop last week is, why is it not .ts? We had a look around. It's because you've already got TypeScript for .ts. So then we come to the Fortran. And so the first thing you'll want to do is stick a use FTorch at the top. Much like you'd be doing if you've got MPI or netcdf, as long as you've linked at your compile time, this is going to pull those FTorch utilities in from the modules, from the library to be capable or usable within your Fortran code. The next thing we're going to want to do is construct some tensors to send data to our model. And the way this is done is we take existing Fortran arrays, so whether it be your temperature, your pressure, your electromagnetic potential, whatever it is you want to send as an input tensor to the model. We're assuming this already exists as a Fortran array, and you then need to generate these additional Torch tensor types. And then you can, when I said before, we kind of have this shared memory. So we need to be able to tell the things that we're sending to PyTorch to look in the same place as the Fortran arrays in memory. That's done through this Torch tensor from array, which is going to generate our input tensors and our output tensors from these arrays, Fortran arrays here. After we've done that, we're going to need a net to run with these tensors. Again, there's a sort of derived type that we've got, which is a Torch model, and we've got a function that's going to load from where we saved that Torch script previously and load it into this object. And so then it's a case of running that model over those inputs to generate some outputs, relatively self-explanatory. And then after we've done all of that, because this isn't quite as clean as Python, we've got to do some sort of garbage collection or some manual tidying up, which is going to be the process of kind of deleting those PyTorch tensors and that PyTorch model that we created and loaded in. The only other thing I want to say here is to briefly touch on GPU acceleration. So I said we make use of kind of the backends that are already within libtorch, PyTorch. The only changes really that are involved are when you're reading in the model or reading in or creating a tensor, you have to now change what was previously declared as CPU. You have to change for whatever backend you're particularly targeting. So here we've got kCUDA, but you could have KMPS, khip, anything else. And as well as changing the sort of target architecture, there's also the option to specify device index. So if you're running on sort of a HPC system or cluster where you've got maybe 2 GPUs per node, you can actually choose to split sort of which device you're sending your work to by specifying the device number here, much as you would within PyTorch itself. The only other thing to note is that if you're running on GPUs, you put the model and the input data on the GPU, but the output tensor is declared on CPU, and this matches the behavior in PyTorch where it will return kind of the outputs you're interested in where you want to be using them. And then just a little note there to say that with HPC simulations, there's going to be kind of some balancing or happy medium to do with operating kind of MPI gather routines. So within running on GPU, the most expensive bit is that data transfer from CPU over to GPU memory. So you don't want to be doing this kind of for every grid cell in your domain. If you're running kind of over several thousand cells, you're going to want to do something sensible like gather 3,000 or 2,000 of them together before you offload that. Okay, so finally, just to say, yeah, we've got a JOS paper. So there's a few more details about some of the implementations and things in here. And if anyone's using FTorch in their work, we do request that they cite this. There's also, as well as kind of the comprehensive examples I talked about, we've got an online workshop that runs through GitHub Codespaces that walks people through. And the advantage of that is it kind of puts you into an environment where much of the kind of the building is already done, so you can get familiar with actually how to use this stuff. So I thought I'd just finish, well, 2 finishing things. The first one was going to be talking about some of the projects we've worked with or some of the projects that have made use of FTorch in their work. So the original place, like I said, this came out of a project where some researchers were trying to couple a parameterization they're developed offline and then use it within a sort of atmospheric model. And they'd done the work. This was kind of purely emulation. So the argument was we're repeating the process that already goes on within the model, but we think we can do it with a neural net to speed up simulation. But they were finding that doing this was orders of magnitude slower than the physics-based process because of kind of lots of data transfer and inefficient coupling. So we worked with them, and this is kind of where the initial groundwork for this came in. It was to speed up the process of the coupling of kind of the net they'd already developed. There was then a follow-up paper on this work, however, which I think is particularly interesting. So this is the Mansfield and Chadri, but what they looked at was to say, we'll take the net that was originally used in this paper, but we'll train it sort of 20 times using the exact same training data. We'll use the exact same training loop. Everything will be identical. The only thing will vary is the random seeds for each PyTorch process. And they found they did this as one might expect. Sort of you get similar R-squared values. If you do your classic kind of geoscience, here's one profile, here's the other profile, they kind of look the same. It looks like they've got kind of identical processes, but they then showed that if you couple these online into the same Fortran model, actually over time, those small numerical differences grow and you get kind of the model moving into different climatologies, showing that you can't just take something that's been done offline and assume that it's safe or standardized when you put it online. Another piece of work was with the German weather model. So this is ICON, which is run by DWD. So we didn't have any input into this work. So this was in some ways quite nice for us, because it showed us that someone could take this software library and use it without us needing to sort of hold their hand through it. They were looking at kind of interpretable machine learning, and it was for a convection scheme that they're trained on a high resolution simulation, and they were hoping to then take this, put it into their lower resolution model, but try and retain some of the benefits that you would get from that high resolution model. So sort of think about maybe running subgrid models or sort of nested models, but without the computational overheads, at least was the selling point. The interesting thing in this paper, I think, was initially that they kind of tried to throw the kitchen sink at it and found that they were getting quite poor performance. But when they looked at kind of the SHAT values, they found that there was kind of an excessive bias towards particular variables, which were sort of violating causality. So things like one of the inputs was maybe updraft velocity, but if you're trying to predict convection, sort of one of the results of convection is enhanced updraft velocity. And so by sort of examining these SHAT variables, removing kind of these non-causal variables, they're actually able to improve the stability and overall performance of the net online. And the other thing to say about ICON is that sort of following on from this work, they're now looking to develop a hybrid model, which is using FTorch as the sort of coupling interface for a number of different parameterizations. But I think that's still work in progress there. So finally, this is some work that I've done with some collaborators at NCAR over in the US. So this is with the Community Earth System model, which is kind of a very large open source modeling suite. And similar to the work that's going on at ICON, we wanted to kind of facilitate easy coupling or easy integration of people who are developing machine learning models into that. And so we've done some work exploring kind of how to efficiently put this into the build system. It's neither CMake nor a make file. It's sort of much, much more involved than that. So we've been working with them to help with this. And part of that on there is that they've got libtorch added onto the software stack on their HPC, which helps with some of the reproducibility there. Okay, so a few other things sort of I won't go into, but you can look at the citations if you want. There was one where some researchers had not kind of scientific application, but just pure emulation. The bottleneck in their code was biconjugate gradient solvers. So they developed an emulator for that. There's some nice work from Will at NCAR, which is looking at kind of bias corrections of CSM. So with the sort of weather forecasting models, things like GraphCast, etc., the reason kind of they perform so well, and people often say outperform the traditional models, is because they're trained on error 5, so they're making use of kind of data assimilation for the training. What Will was looking at doing is actually comparing model biases from CSM to error 5 by doing a series of historical runs, and then seeing if it's possible to kind of learn the corrections as kind of a post hoc process. There's also some stuff with the WaveWatch 3 model. There was a paper that came out, I think, earlier this week, which is the NVIDIA one, looking at, again, embedding convection resolving model within E3SM, so kind of trying to get that nested model advantage without the expense. And then a couple of other bits of work that are kind of ongoing there, but interesting things to read if people are so inclined. So the very last thing that I want to talk about is sort of where we're looking to go next with this work. This has been largely kind of spearheaded by Joe, who's also at ICCS, and has been doing, sort of has a good background in automatic differentiation, process within models. So automatic differentiation is, for those who might not be familiar, is this idea that you can run some code, sort of write some code, run it, but then when you get to the end, you say, what would it look like if I differentiated that code and got gradients for things working through? So this is how neural nets work. So we propagate through matrix multiplications and then get gradients and work backwards. But it's not strictly limited to that. You can also do this for just generic code. So there's the PETSI library is quite popular, has been doing this before machine learning came popular, because it facilitates a whole bunch of things other than just machine learning. And so the reason sort of this has been particularly interesting is, like I say, this work that showed that even if you have nominally identical models offline, your performance online is slightly different, or can be different. And there's been sort of a rise over this last year looking at this idea of kind of differentiable models more broadly. Sort of, can we differentiate through an entire climate model or through a subset of that climate model to do things? So the nice things about this, like I say, is one thing is it potentially avoids you saving large volumes of training data. So if you want to train something for a climate simulation, you need to run that climate simulation, save huge volumes sort of for these greedy algorithms, train something, and then possibly throw that data away at the end. Sometimes it's more useful, sometimes it's less. The other thing that's quite nice is, and I'll talk about in a moment, is this ability to expand kind of loss functions. So often we're writing a neural net that takes some kind of physical inputs, but we're then generating sort of some more abstract outputs, such as grid cell tendencies or grid cell fluxes, whereas the thing we're sort of actually genuinely interested in is computed slightly further downline from this. So perhaps it's kind of surface radiation or it's precipitation, sort of thing. And so actually being able to have a loss function based on what we're really interested in would be nice. So the slight downside to this, like I say, is it's quite difficult to implement. So as I say, PETSI has been going on for a long time. There's various other frameworks as well in a variety of languages. So the idea of this expanded loss function, like I say, if you want to calculate something, a loss function based on some kind of variable that's downstream from the exact output of the neural net, you need to be able to differentiate through whatever's between the end of your neural net and the thing you're interested in. And so by exposing sort of the autograd properties should hopefully allow you to do this within the Fortran. In terms of implementing this, broadly speaking, we sort of follow a similar approach to the rest of FTorch. We make use of the fact that automatic differentiation is already sort of a key feature of libtorch, PyTorch. And so we provide an interface to use those things that are already available here. The slight nuance is that there's a bit of extra work that's required. So because we want to kind of be able to do this without people worrying too much and sort of adapting or writing what looks like native Fortran, we have to overload all of our mathematical operators that might be being used. So now, rather than sort of multiplication being multiplication, we need to add into Fortran something that says, here's what you do if you have multiplication for two torch tensors, do that accordingly. So yeah, using automatic differentiation, as I say, it's very similar. You create the tensors as you would have done previously, but now you've got this additional option to specify that you want the gradients to be tracked, very similar to PyTorch. You can now call some kind of mathematical operation. So these are torch tensors, but because we've got these overloaded operations, it's going to know that it should track the gradients through those processes, creating intermediate tensors as appropriate. We've got the backward step, which is going to generate those gradients. And then we've got a function that will pull those gradients out if you want to look at them within the Fortran. Coupled to this, and this is very much work in progress, so the pull requests are currently open. We're hoping to get these merged soon, but is adding in some kind of wrapping for torch optimizers, allowing you to kind of perform steps and conduct optimizations, again, using things that are already within libtorch, PyTorch, so stochastic gradient descent, the weighted atom, etc., etc. And then whilst we've not yet built in any kind of more elaborate loss functions, we have got the sum and the mean, which kind of the most useful, at least at kind of a basic level. And so putting it together, this is where we sort of got to so far, is trying to train a tensor of 1, 1, 1, 1 to predict 1, 2, 3, 4. So just the straightforward dot product or matrix multiplication, and we use a loss function, which is just the mean squared error. And we're then using sort of an optimizer to drive this process through a loop. And the nice thing we have is that we do get to the answer we want. And if we do a comparison between both the FTorch and the PyTorch code, they're following the same path, generating the same numbers, which is good. So what are we hoping to do with this? We've got kind of a case study that's going on with UKCA. This is, I think, a really nice application of machine learning in science because it's not going to affect any of the science. So currently, within UKCA, it's running kind of a very, very intense, computationally intensive process over a series of grid cells to do chemistry calculations. The way it does this is it starts off, performs a time step, does this for all of the points it's been given, and if it doesn't succeed with any of the points, it will then halve the time step, go back to the start and run again. If it fails to converge again, it will halve the time step again, go back to the start and run it all again. And so this is currently kind of one of the biggest bottlenecks, and there's no other more intelligent way of doing this because it's not a straightforward way to predict what the optimum time step should be. So the idea is that we might train a neural net to predict that time step. This is, like I say, as long as it predicts the right time step, it's not going to change any of the science. It's not a new scheme. It's not a new calculation. It's all the same code that's going to be running. There's also the fact that this kind of time step data isn't useful information. If we want to save all of this out to train a neural net, it's kind of huge amounts of data, simulations that aren't likely to be used for anything else. So if we can do this online while simulations are already running, it's also going to save us that overhead. So that's where I think I'll finish up. There's some summaries up there, but people have the slides. I'll just leave the slide up here and say I'm happy to take any questions.
I have a question about deployment.
Mm-hmm.
So on HPC, if you were deploying one of these hybrid models, would you have your traditional Fortran code running on the CPU nodes, and then you have the GPU nodes to one side that's handling the parameterization, or how would you do it?
Yeah, that's a good question. It depends what you want to do. So if you have a very, very simple model, that is just maybe, I think, so some of the earliest nets in this work were maybe feed forward 5 layers. It's not, from what we saw with that, it's not going to be worth trying to run it on a GPU because you're going to lose so much in kind of collecting data, sending data, that just run it. And unless you're talking about collecting huge numbers of grid points, you're better off just running it on a CPU. If you've got more involved things, so the paper that came out about a week ago did show that actually they got sort of huge amounts of speed up by running the parameterization on GPU. Then yes, it's the case that you would have your Fortran model running on the CPUs, and then you'd at the appropriate point in the code, you would target the tensors and the model, put it on the GPU, and like I say, do something sensible with your MPI to get kind of the lowest data transfer overheads you can. There is a discussion to be had. I think this is more broad than what we're doing, which is to say what the most, I guess I would say environmental efficient, but also if you're paying the power bill, economically efficient, I suppose. But to say that if you've got a parameterization, this is potentially putting a blocker in your code. So you're going to be running lots of stuff on CPU at full capacity, and your GPUs are going to be somewhat idle. You're then going to hit kind of this block. Your CPUs are going to go somewhat idle. Your GPUs spin up to do the parameterization, and then it flips back. So I think there's also questions to potentially be asked around that. And it's something I think we're trying to encourage researchers is to kind of speak to those who are maintaining the models, developing the models early in their work to work out what a sensible approach for kind of operational uses. So the other example I've seen more recently is a lot of these parameterizations, particularly in climate models, operate on kind of single grid box levels. but we know that the atmosphere isn't a series of grid boxes. It knows about everything around it. So there's a lot of talk about kind of non-local schemes. So allowing sort of parameterizations that will know about other points on the globe. The difficulty with this is if you've kind of chunked your data up and distributed it to lots of nodes, allowing them to communicate with each other can get quite expensive. And so we've had kind of a number of researchers who've come along and said, oh, I've trained this amazing new scheme. It takes my entire global grid in and produces amazing predictions. But we've sort of had to talk to them and said, you could implement this, but you're gonna, if you're gathering sort of data from 30 nodes onto a single process, running a net, sending it all back, it's probably going to be sort of so hideously expensive that operationally people probably won't be interested in this. So yeah, encouraging people to talk early on. Yeah.
Yeah, just go into the kind of final thing you said about that missing up. Trying to guess the longest time step while the Newton method search. How does that work? What does the machine learning model look at? Is it the state variables or?
So this is mostly work that's being done by Joe, but I've been working with him on some of it. So the idea is that you will take the sort of anything that would have been an input to that scheme and just throw it at it a bit like a black box, because like I say, it's a relatively safe application, so we don't really mind how it gets the answer. That said, often the correct time step is the one that it initially starts with. And so there's been a lot of stuff I know he's been doing to try and filter the data, to bias it, to kind of not just always predict the normal time step. And I think he's also been trying to do some way of gauging what sort of variation in which variables cause the most variation in the time step to restrict this down. But I would, yeah, drop Joe an email to find out more about that, would be my suggestion.
So the lesson in some ways, I was wondering implicitly to what extent it's going to just end up to some degree emulating the solver to find the right answer. But I mean, probably not much. But those humans can look at the thing.
So
that looks like too long a time step, doesn't it, without actually solving the problem?
Yeah, so but I should also say at the moment there is no solver for time step.
No, I know.
Oh, so yeah, so what we're trying to do is predict what the most sensible time step would be for.
Yeah.
But yeah.
One, the short one. So I'm guessing once you're working with your modeling in Fortran, based on what you said, there's basically no performance difference over than using PyTorch in Python, because you're just calling the same libraries, C++ libraries. Is that right?
As in, if we were to,
For example, the last thing where you were training with the new functions you've added to be able to train a model,
yeah,
that wouldn't be any slower than doing it in PyTorch. Yes.
We've not got as far as checking that. I would hope not.
Yeah.
If anything, maybe a little bit faster, because you're not worrying about kind of the Python overheads. But I've not. Yeah, we haven't checked that. One thing we do want to do is kind of do a bit more benchmarking of the code. So we've done a few comparisons to things, but it would be nice to have sort of some more concrete examples, especially providing guidance for people over sort of what process to employ for what data sizes, this sort of thing. But yeah, it's not something we've definitely looked at yet.